So, good evening to all of you. We will start with the topic called CMR, that is carbon magnetic resonance. Yesterday we have discussed about the proton magnetic resonance. Now the principle wise, it is exactly same. What is the principle of proton magnetic resonance? That is, in broad sense, we call it as NMR. When a nuclei having a half integral spin at their own axis, it considered to be a bar magnet. That means it produces magnetic field. When placed in a strong magnetic field, according to the Zeeman effect, the energy levels will split it. Okay, so let me just show you the first diagram once again. Okay, so it will split into the plus half and minus half as the Zeeman effect, and the energy gap depends on the magnetic field used. That means the source radio frequency used for the resonance purpose. Now look at here. The second diagram we have discussed, that is a gyromagnetic ratio. There, the gyromagnetic ratio for the proton is 42 something. That is 4 times more than the carbon. So today we are going to focus on C13 nuclei, where the gyromagnetic ratio is very less, as well as their abundance in nature is also very less, that is up to 1% only. So the sensitivity wise, the C13 NMR is going to be less sensitive than Proton NMR. So this is one thing. Another thing, the Proton NMR suppose works on 40 megahertz as a frequency. That means the required magnetic field for 40 megahertz will be more as compared to particularly in case of C13, the required frequency will be 4 times less. That means it's 1000 megahertz only. That means in simple language, for C13 NMR, required magnetic field will be less than proton NMR. In simple language, like always there is a confusion. We are talking about the magnetic field and the applied resonance frequency. So they are directly proportional. So suppose if I say the required magnetic field is more or less, that means the frequency will be more or less. So it is directly proportional. So in simple language, the magnetic field required for C13 will be less as compared to the proton magnetic resonance. So this is a simple difference between the proton NMR and C13 NMR. The best example I will let you know. If I wanted to record my proton sample on 400 megahertz, and again, same sample I wanted to load for C13, then the magnetic field required for the C13 will be 100 megahertz. That means the source will be 100 megahertz as a frequency. So this is the basic difference in between proton magnetic resonance and C13 NMR particularly. Now look at here. In case of C13 NMR, what basic things we have to consider? Everything principle wise is same. There is no any difference in terms of the principle. The only thing is that the coupling constant in terms of proton magnetic resonance is varies from up to max is 20 hertz. 20 hertz is very much high. If you see the cis geometry or trans geometry, the cis will having 5 to 10 max, and trans will be 11 to 18, and max 20 in case of the aromatic structure or cyclic structure. But if you see the C13 NMR, the coupling constant varies from 100 to 250 nanometers. So this is a basic difference between the proton magnetic resonance and the C13 NMR. Now, why it is so? If you see the proton magnetic resonance, we have discussed the magnetic field required is like suppose 400 megahertz instrument I'm using. So the required magnetic field is absolutely the same. Suppose I wanted to switch over from proton to C13, the magnetic field required will be 4 times less. That means if the instrument is working on 400 megahertz, then automatically the instrument will go to the 100 megahertz. That means the denominator, you can see denominator is the magnetic frequency particularly, or instrumental frequency. So that is 4 times less. So the denominator is going to be less. So the del value in the simple formula will be high. Our formula, particularly simple formula yesterday we have discussed was that del is equal to is nothing but the ratio. Del is equal to the ratio of what? This is a frequency, that is observed frequency H said, okay, which is measuring and applied magnetic field.
Zero, यानी ये diamagnetic होता है. Zero.
Please mute yourself.
Root
Please
3
mute
upon
yourself.
3. यानी 5, 15. Root
Guys,
15 ना?
please
Right?
mute yourself.
3 root 5.
तो इसमें color कौन रहेगा?
Okay, somebody is having discussion and their mic is unmuted. Okay, look here. This is a applied frequency in terms of the magnetic field, you can say, or it's a radio frequency, so which is in megahertz. Now this frequency required for the C13 will be less. So the denominator will be less. So del value for C13 will be high. So the starting del value will be 10 and it will reaches up to 200, 210, 20. So that means the scale for chemical shift values for C13 is used is just because of the what? The required magnetic field is 1/4 to that of proton magnetic resonance. So if you see the scale for the C13 NMR, it will be again changed. So as the required magnetic field is less, the coupling constant is going to be very huge. And that is going to be a drawback in case of C13 NMR. Now, what is the coupling constant? The coupling constant is nothing but the spacing distance. Suppose we have a doublet. Now, simply I will draw one spectrum over here. In case of, suppose proton magnetic resonance, just imagine this is a below one is a proton magnetic resonance, and we got here doublet, and their coupling constant is roughly like 7, 8 max to max. But here in case of C13 NMR, so the coupling constant is 100. That means the spacing distance will be this much. Now, suppose we having here doublet of doublet. So this doublet, suppose this is one doublet and there is another doublet. Okay. So these two peaks will merge together and no one can understand which one is which peak. So we will see this peak or this peak. So this is a mixing of the splitted peak and it will be a it will be a drawback of C13 NMR because of the spacing distance is very huge. So you cannot get the exact information about the splitting pattern, that is the spin-spin coupling. So that's why we'll see one by one. So this is one of the prominent thing in case of C13 NMR, that this is a less sensitive than the proton magnetic resonance. This is one thing. The required magnetic field for C13 NMR will be less. That means the required radio frequency will be less. So the denominator will be less. So del value will be high. So the del value will be ranging from 10 to 200, 220. So this is another prominent difference. The first order equation n plus 1 is applicable absolutely with what? The nuclei attached to the carbon, because carbon is having a half integral spin as well as proton. So the carbon may couple with the proton. So according to the n plus 1 rule, so there is a coupling with the proton. The carbon will couple with the proton. So simply, Mr. Borse, can you please unmute yourself? There is a disturbance. Who is that, please?
Is the sum of several delicious but complex parts.
All right. Now look at here. So we are talking about that the required frequency. So required frequency, obviously, it varies with the sample. Now, the application of the splitting pattern will be exactly same, where the carbon will couple with the proton. And you will get the same pattern like n plus 1 rule as that of in case of proton magnetic resonance. Now here, most of the C13 NMR will give the accurate information about the carbon contents. That is a quantitative as well as qualitative measures of the carbon containing things. So most of the instruments, they are coupled as a proton decoupled mode. So they don't study proton coupled because of the drawback that coupling constant is very huge and you cannot isolate the splitting pattern correctly. So most of the C13 NMR peak will be a single line. So line spectrum, we can consider this C13 spectrum. More to the next. As I told you, the principle wise, it is absolutely same. Now look at here. As I have mentioned, this instrument is considered to be less sensitive than the proton magnetic. So the noise in case of recording the spectrum will be more. So you have to give the more scanning, that is we called as the that seaming in terms of the instrumental operation. So the more the seaming, lesser will be the noise. So in case of the C13 NMR, the scanning will be more. And nowadays, all the techniques in case of IR or maybe the NMR, there is a Fourier transformations where the noise is eliminated by taking simultaneously n number of spectra. Before it was like that, we have to record the spectra simultaneously, we have to tune the frequency, we have to change the magnetic field, and then slowly the peak as well as the noise will have their intensity. So it was confusing in the olden time, but now the technique is modified that at once we are going to record it like 100 or 200 or 1000 spectra, and there is a mathematical operation, the number of spectra, the noise is equal to the noise equal to is the square root of the number of spectra. So more the number of spectra, the noise will be less. So it's a square root. So that means in the olden time, we used to have this type of spectra, that is with a single run. Now it is a run with 200. So at once 200 spectra will be recorded, and here the noise will be very less, and you will see prominent peaks of the carbon. Whereas in case of the first case, it is very difficult to work out which one is our prominent peak of the carbon. So let's see what exactly the NMR related to the carbon. As I told you, it is absolutely applicable to the n plus 1, that is the first order equation, as the carbon couples with the proton. So in proton coupled spectrum, what you will see, if there is a CH3, then 3 protons are attached to the carbon. That means 3 proton is a neighboring group. So N is equal to 3, 3 plus 1, 4-line spectrum will be getting for methyl group. If you're having a methylene, that is CH2, 2 plus 1, that is a 3-line spectrum, that is a triplet type of thing. If you're having a CH, that means there is a 1 proton attached to the carbon. So N plus 1, that is a N plus 1, that is a 2-line spectrum, that is called as a doublet. And if there is no any proton attached, that is a quaternary carbon, then you will get a single line spectrum. So this is a spectrum which is proton coupled, where the carbon coupled with the proton, and you will get the big spec like triplet, quartet, and the spacing distance is very huge because the coupling constant is going to be in 100 or 200 range. So this is applicable, no doubt, but the normal study in case of the experimental, we don't do this type of proton couple analysis. So there is a proton decouple which is widely used in analysis of C13 NMR. As I told you, the drawback, that is a coupling constant. Now look at here, the first spectrum, which is the proton couple, where we got here triplet for the CH3, triplet again for CH2, and triplet for the another CH2. And the aromatic protons will be as a bunch of pig. So here, how many exact carbon atoms are present in the sample, we will not have the correct informations. But in case of proton decouple, you will get the exact quantitative measures of the containing of the carbons. Those carbon which are equivalent, they will show the same peak, that is again same as that of the proton NMR. But the slight difference in the field will show you the line in the spectrum, and that counting of the line, you will get the exact count of different types of carbon present in the molecules. So this is the proton decouple, which is normally used in interpretation. So interpretation of the spectra will normally provided with the proton decouple. Nobody will provide it with you proton couple. So this is one thing you have to remember. Now there is a modification of the proton coupled spectra to off resonance decoupling, because there are some instrumental arrangement where the coupling constant has been reduced and the peaks which observed will be exactly following the N+1 rule with the same pattern of splitting. Now look at here, as I mentioned here, the required magnetic field for the carbon to couple or flip is very low as compared to the proton. So that means denominator is going to be a less. If the denominator is going to be a less, ultimately the del value is going to be very high. So that's why the del value for the C13 NMR is ranging from 0 to 210 and 220. Now here this is a chart where you have to sometimes you have to practice this chart, or you should know this chart, the rough range of the alkyl groups or the carbon having the functional group, like maybe the carbonyl containing compounds, or maybe the alcohols, or maybe the ether, or maybe the halide. So all have the ranges. Like take the example of carbonyl compounds, they will be falling around 160 to 210, 20. So if you compare this carbonyl compound like aldehyde and ketone, they are the highest coupling, that is a del value containing carbons, that is ranging from 180 to 210. Most of the cases aldehyde and ketone will show you 200, 210. If we see the carboxylic acid, amide, and ester, they will be lower than this. So it may be sometime 180, 185, 170, 175. So these are the carbonyl values, the carbon having as a carbonyl carbon. If you see the benzene ring, benzene ring also considered to be desilted because of the, as we have discussed yesterday, because of the pi bond. So the del values will be ranging from 110 to 116, where the quaternary carbon over here will have higher chemical shift value. If you see the olefinic double bond, again, olefinic double bond will have anisotropic effect, and because of that, the values will be as that of aromatic ring. So it will ranges from 100 to 150. If you're having a triple bond, again, we know that triple bond values are less than the double bond, though there is a more S character, but because of the anisotropic effect, these values are lower, at 65 to 85. And the rest of the values like alkyl halide or alkyl group like primary, secondary, tertiary will ranges from 10 to 15 to 20 depending on the environment of the carbon. So if you see, this is the chart, so you can just work it out. Again, the factors are affecting the chemical shift value is because of the electronegativity as well as hybridization of the carbon. And most of the carbon chemical shift values ranging from 0 to 220. Now, if you see here some of the values may have the 0 chemical shift value. Look at here, one of the value having the iodide, that is the iodide is considered to be a metalloid because of the high polarization. So because of the polarization, you know that metal is considered to be electropositive. As it is electropositive, it is highly shielded and their chemical shift value is going towards the 0. So this is a simple reason why the iodide halide, the iodide containing halide will have a lower chemical shift value as compared to the chloride and bromide. This is again the chart. You can just work it out. You will get easy idea about how the chemical shift values are changing. Now look at here how the spectrum, C13 spectrum, particularly the proton decoupled, we're talking about proton decoupled, looks like. Now this is a single line spectrum. Whatever carbon is there, that carbon, if it is a different in environment, it will show a single line. Depends on their electronic environment. If it is having a strong electronic environment, if it is a nearby an electronegative atom, then obviously their chemical shift value is going to be shielded as that of Proton NMR. So again here TMS is going to be a standard and rest of the thing is exactly the same as that of the Proton NMR. Now look at here, this is 2-butanone. 2-butanone will have the carbonyl carbon peak is 208, whereas the methyl and the methylene protons are towards the 0. That means they are shielded. Suppose if you see the C4, which is away from, that is attached to the CH2, which is less de-shielded, that means it is shielded, and the methyl group attached to the carbonyl group, as we know that carbonyl group is considered to be electron withdrawing because of the electropositive characters of the carbon. So the carbon attached to the carbonyl carbon is considered to be more electronegative than the carbon attached to the carbon of alkyl group. So that's why here C3 and C4 is highly shielded, de-shielded than the C4. Now look at here, another example, para-bromoacetophenone. If you see here, C2 is a carbonyl which is around 200. C1 is going to be towards the attached to the carbonyl group. So it is something like 20, 25 in range. If you see here, aromatic carbons, they are above 100 or 110 or 120, where the C3, which is the quaternary carbon, and C6 is going to attach to the bromide, which having a different field. Okay, so the quaternary carbon attached to the carbonyl carbon is considered to be more de-shielded, and the carbonyl effect will be on the ortho position as well as on the para positions. And bromide is considered to be electron-rich species because of the lone pair of electron. So it does not have that electron withdrawing effect like C3, C4, and C5. So that's why C6 value is comparatively is less than the other. Look at here, some of the, as I told you, not all the carbons will show you the line. Why? Because some of the protons, they have the same environment. Like take the example of this methyl cyclopentane. So this methyl cyclopentane will have how many different carbon atoms? So there are different carbon atoms. Like if I would show you, this is a different one. This is going to be different. This one and this one is same. This one and this one is same. And there is a plane of symmetry across this. If I draw here plane, so this one and this one is same, this one is and this one is same. So total number of lines will be showing in the C13 spectrum will be for this one, this one, this one, and this one. That is a 4-line spectrum. You see here, this isopropyl ethyl ketone, where these methyl groups are same. So they will show a single line. Whereas this 1, 2, 3, 4, 5 line spectrum you will expect it for this compound. If you see here, this this olefin will have this methyl group and this methyl group absolutely different. Why? As I told you, vinyl chloride, which is having a cis and trans environment with the chloride in the similar fashion, this methyl group is nearby to this methyl group. So in a simple language, you can see here, this methyl group is close to this, whereas this methyl group is trans. This is close to the H. So obviously this environment for this proton and this carbon will have a difference. So all the carbon present in this molecule will show the line. 1, 2, 3, 4, 5. So the 5-line spectrum you will expect it for this type of molecules. So you have to see the symmetry and the electronic environment across the molecule. Now look at here, these simple molecules where this on eliminations with the alkali, what you will get double bond, and this double bond sometime it may be in the ring or it may be the outside. So it is not possible to guess which type of product you will expect. But if you simply take the C13 NMR spectrum for this type of molecules, this one and this one is absolutely different. Why? Because this will give you more line and this will give you the less line. Because if you see here, this one is completely different than this green will be same, this pink will be same, and this will be different. So 1, 2, 3, 4, 5 lines you will get for this compound. Whereas if you see this molecule, you will get 1, 2, 3, 4, 5, 6, and 7. So easily you can work it out by just looking at the C13 spectra, which product you are getting. If you are getting more lines, so you will getting this product. If you are getting less line, you will getting this type of product. So this can also monitor the chemical reaction. Now look at here. This is another molecule, orthoxylene, where there is a straightaway plane of symmetry is there. So the half of the carbon will show you the line. So 1, 2, 3, 4. So 4-line spectrum is expected for orthoxylene type of compound. Now look at here. This is a highly symmetrical compound. So if I put a plane over here as well as over here, so all this methyl group, they are considered to be the same. And obviously this olefinic carbon will again same. So methyl carbon, all methyl will be having one line, and this olefinic carbon will have another line. So because of the double symmetry, this molecule will show the 2-line spectrum. So number of times the molecular structures will have a symmetry, and then you have to work out with the C13 NMR as well as with the carbon, as well as in case of the IR as well as mass. So one spectroscopy technique is not sufficient to give you the correct information about the structure. Now, as we have discussed over here, most of the cases, what we found here, if you see the spectrum over here, you will get a line. Now, this is C4, C1, C3, these are the line. But when we look at the structure, we will get confused whether this C4 belongs to CH3 or this is CH2 or this is CH3. So this type of informations can easily acquired by the modification of the C13, and that C13 has been modified into the DEPT spectrum. That is also the part of C13, where there is a modification. There is a odd and even number of the proton containing spaces like CH3, CH2, and CH. That means if you see the CH2, these are the even number of proton, and odd number is CH3 and CH. So odd and even is polarized in a different angle through 45, 90, and 135, and you will get the peak appeared in the C13 spectra in a different fashion. So you can directly come to the conclusion that this compound possesses CH3, this compound possesses CH2, this compound possesses CH, or having quaternary carbon. So the distortion-less enhancement by polarization transfer C13 NMR will give you the accurate information about the alkyl group present in the molecules, including the quaternary carbon too. So this is considered to be another vital tool in spectroscopy technique to give you the correct information. As I mentioned, one single C13 NMR is not enough. So most of the cases, the C13 NMR is coupled with the DEPT data. So that DEPT data makes the analysis of the C13 peak very correctly in terms of getting the correct structure. Now look at here, this particular compound like methyl ketone, where you will find that there's a CH3, there is a CH2, and there's carbonyl carbon, which is a quaternary carbon. Now, if you see this DEPT spectrum, so the DEPT spectrum for the odd and even number of carbon having proton will give you the different orientations in the spectrum, and how that looks, that I'll show you. Now look at here, there are, as such, there are 4 different DEPTs. One is, in fact, over here we have shown prominent one, that is a DEPT 90, which gives the correct information about the CH. Now, in case of DEPT 45, if you want to record DEPT 45, so the DEPT 45 gives the correct information about the quaternary carbon. Rest of the peaks will be there, only the quaternary carbon will be missing from the spectrum. Whereas in case of DEPT 19, all the peaks will be missing except the CH peak. So the only one CH peak will be appeared in the spectrum. Whereas in case of DEPT 135, where you can see the CH2 peak, which is in the negative format, that will be falling below, and positive peak is above the line, that is CH3 and CH. Once you confirm the DEPT 90, CH position will be absolutely known to you, and then the rest is your CH3. So by just working out, you can easily get the information about the alkyl group present in the molecules. Now take the example of this one terpenoid. This terpenoid will have a number of CH groups as well as CH2s and CH3s. Now if you see here, this can give the correct information about DEPT 45 also. So the DEPT 35, if you record, the quaternary carbon will be missing. That means this C6 over here, this is a quaternary carbon that will be missing, that cannot be seen in the spectrum. Whereas DEPT 135 give the correct information about the negative peak, that is for CH2. So there are 4 CH2s in this molecule. If you see here, this is CH2, this is CH2, this one is CH2, and this one is CH2. There are 4 CH2 that falling down over here as a negative peak. There are CH. Now 19, DEPT 19 give the correct information about the CH peak, that is methine, that is this 7th one is CH peak. Another one is carbon 2, and there are 4. So there are the 3 carbon which is having only one carbon, only one hydrogen. So this is CH methine peak. So there are 3 methynes. Now if you subtract this methine proton, like this one is subtracted, this one is subtracted, this one is subtracted, the rest is this one and this one, remaining is 2 is CH3 peak. So there are 2 CH3s. Which are those? So this one and this another one. So there are the 2 different CH2s, which peak is absolutely close, because of this CH3 is close to OH, and this is something this. So the environment wise, this carbon will having 2 different methyl group, but they are not same. They are having a different orientation. That's why you will get close peak. So because of the DEPT spectrum, it is very much clear to you that you can work out the CH3 peak very clearly, CH2 peak very clearly, and CH, as well as quaternary carbon. And that is the correct information you require. Now look at this particular isopentyl acetate. So what this DEPT shows you, that there are 2 methyl groups. So there are 2 methyl. This is a methyl, the CH2, so methylene, that is CH2, and above R it may be CH3 and CH. So that you can easily work out. So there is only one, that CH2 is methine, and rest is the methyl group. Okay, so it is very easy to work out how the methylene, methine, and methyl carbons falls in the DEPT spectrum. So this is very informative spectrum. Now look at here, one of the spectrum I just picked from the book. Now, this spectrum has clear informations. Now, look at here the structure. I'm not going to just discuss about the analysis, complete analysis, but just for understanding point of view, how the spectrums will be provided to you. Now, look at here. We are talking about DEPT. So, DEPT data is already provided to you. Now, it is mentioned here CH2 is peak is negative, CH3 and CH peaks are positive. So, this below one, they are the CH2s. And then easily you can work it out the CH peaks from the top. So this way, the reading of the C13 spectrum will be very, very easy. You can easily work out, you can easily identify which group is which. Now from the C13 also, Proton NMR also, you can easily work out which one is a triplet, which one is a quartet, which one is multiplet by looking at the expansion spectrum. The same spectrum will be shown in expanded form, and that can be easily worked out. You have to actually measure this height of the, this is integral height of the peak in millimeter, and then you have to add all together, and then you have to take the ratio with the molecular formula that we will see in latter half, how to comment on this analysis. So this is how the C13 is useful for characterization point of view, as well as Proton NMR. So this Proton and C13 is the core information about the structure. This gives absolute structure about the attachment of the group of atom present in the molecules, because your UV is just giving you the very rough or crude information about the chromophore. It may be present, chromophore. That chromophore is what? Maybe the double bond is present, okay, or there is a pi to pi star or n to pi star. So it is a maybe, it's not present, absolute present. I give the little bit absolute information about the functional group. That functional group can be comment concretely that, okay, this is the functional group present. If there is a carbonyl stretching frequency or NH or OH stretching frequency is given, you can absolutely comment about the functional group. But what about the rest of the group present in the molecule? And that rest of the group present in the molecule, that may be the aromatic ring or that may be the alkyl group present. So that information is absolutely given by the C13 as well as Proton NMR, which shows clear joining, which group will join with which, and what will be the probable structure. And that probable structure you can confirm by using the another spectroscopy technique that is we call as mass spectrometry. Mass spectrometry gives the absolute configuration or absolute confirmation call about the structure. Now this UV, IR, NMR will give you the crude information about the probability. Now this is the probable structure, but the confirmative test will be because of the mass spectrum, and mass spectrum will give the confirm idea. Okay, yes, this is the correct structure because it shows the mass peak and the fragments following that particular where you have joined in NMR. So that fragments and the molecular ion peak give the correct information, and on the basis of mass spectrum, you can confirm, okay, this is the correct structure. Otherwise, you will have to mention these are the probability or probable structures. Now, let's move on to the next spectroscopy, that is mass spectrometry. As I mentioned, mass spectrometry is going to be a concrete information about the overall structure. That means the molecular ion peak. Now, the molecular ion peak is nothing but very, very crucial information. Most of the cases it happens, you know, when I was working as a PhD student, I got NMR, absolute NMR, I got IR even, but mass was not matching with the structure. I struggled for a long time, but when I come to the X-ray crystallography, I come to know that I got a rearranged product. So that means my mass was correct. Mass was telling that whatever NMR you got, which is absolute NMR in terms of C13 as well as proton, but there is a missing something because the structure which I proposed was not matching to the mass, and that mass is considered to be a confirmative test. And that crucial spectroscopy technique we will discuss, which is very, very simple. Now, what is mass spectrometry? Now here, normally we are not going to use any light source. Okay, we are not going to use any light source as that of UV, IR, NMR, where we're going to use here electron gun. That means one certain potential or voltage having electron we are going to use to ionize the molecules. You know that covalent bond or pi bond or non-bonded electron will have a certain energy. If you put some energy across this molecule, the bonded electron will eject out because of the electron gun. So we are going to remove one electron from the pi bond or from the non-bonded electron or from the sigma bond. When we remove one electron, the remaining electron will be with the molecules. I will discuss with you that later. But what is exactly this mass? Why we call as a mass spectrometry? Because it gives the correct information about the mass of the molecules. That is a molecular ion peak. That's why we call this spectroscopy as a mass spectrometry. You are getting the correct information about the mass. It is also called as positive ion spectra or line spectra. This is also called as line spectra or positive ion spectra, because in this mass spectrometry, we do analyze the cationic species. We do not study radicals or anionic species. Mostly the positive charge fragments we are going to analyze by means of mass spectrometry. Now, what exactly mass spectrometry? The basic thing is what? Basic thing is this spectroscopy is considered to be a destructive technique. Very much understand. Our IR, our NMR is non-destructive technique, means the sample which we use for analysis purpose can be restored back and we can use. Okay, we can recycle or we can reuse that sample. But in case of mass spectrometry, the sample will destroy because we are going to bombard that molecule with the electron gun. So the molecule gets fragmented out or destroyed in the spectrophotometer. But the more beauty of this spectrum is the sample required is in ppm level. Okay, ppm level, that is very, very fine. Like if you have a capillary, if you just dip into the your sample, any diluted sample, and take a methanol vial means a small the tube or small vial, and just dip into that, and that is enough. That ppm level of solvent is enough to analyze the mass spectrum. It requires very, very dilute solution. Now, what exactly the basic of this? Basic is what? The sample will be ejected in the mass spectrum, and then the electron gun will be bombarded on the sample. The sample will go into the first gaseous state, and then gaseous state, the electron gun will be bombarded on this sample, and the one electron will be bombarded. The one electron from the sample will be ejected out. So the two electrons will go out, and the ionized molecule will goes into the mass spectrum, and then the mass spectrum will make the fragments of these molecules, and the mass analysis will take place, and then ion detection will take place, and then analysis will give you the spectrum. So this is simple, the technique. Now here, what we're going to study? We're going to study the ion which is formed, the positive charge ion which is formed to the charge, the mass of that positive ion plus the charge, whether it's a monopositive or dipositive. So the mass to the charge ratio is going to be studied in case of mass spectrum. Now here the unit for the mass spectrometry is m by z or m by e. E is called as charge, or z is also called as a charge. So mass of the fragment is nothing but the mass, how we calculate atomic masses together, we'll get the mass of that fragment. And whether it is a positive charge once or twice, divide by that charge. So in most of the cases, there is a positive charge, one positive charge. So whatever mass of that fragment is there, that mass is considered to be m by z. And that m by z gives the correct information about the structure as a whole, as well as the fragment of the molecules. There are different mass ionization techniques in mass spectrometry. So there is a EI, there is a CI, there is a ionization, chemical ionization, there is a electron ionization, there is a fast atom bombardment, there is a plasma desorptions, there is a matrix, that is a MALDI, which is very much famous in getting the correct spectrum, MALDI, and the electron spray. These are some of the technique which used for ionization purpose in the mass spectrum. Now let's see what is the useful things for us. The mass spectrometry, here the high electron gun will use, as I told you, and that taken out one of the electron from the molecules, and then you will get the first information about the molecule as a molecular ion peak. And that molecular ion peak is very much informative for getting the correct structure. So this is a simple mass spectrometer where this is the inlet where you can insert the sample, and then here the sample will be converted into the gaseous form, and then electron gun will be bombarded. The molecule will get ionized. There is ionizations. So the ionization potential, that is a 10 to 15 volt electron, is sufficient to ionize the covalent or pi bond. Mostly we highly energetic is covalent bond. The pi bond is less energetic and non-bonded is further less. So when we eject out one electron from the sample, the molecule become ionized, and then what will happen? The molecule become inactive. So there is a technique to accelerate the activity of this molecule, and then that molecule will be pushed into the spectrophotometer, and there is a magnetic field. Because of the magnetic field, here the acceleration takes place. That means the charged molecules will be move very fast, and then when any charged body, when spin at their own axis very high RPM, they produces magnetic field, again like a NMR technique. And then when this sort of charged bodies entered into the spectrum, what will happen? The magnetic field will attract that charged bodies. And then the bond which is ionized undergo fragmentation according to their stability. So the charged ion, that is a cationic species, which is, the carbocation stability. The natural rule of carbocation stability will be applicable. And according to the stability, the fragmentation will take place. But that fragments will be studied under the detector, and you will get the line spectrum, and that line spectrum will be the bar line type of spectrum, which will be I will show you in a minute. Now look at here what exactly we do. So this is a molecule which is under study. When it is bombarded with the electron gun, this is the electron we are going to bombard on the molecule. So this molecule is taken out one electron. So the one electron will go out. That means there will be two electrons over here. So this one electron over here, when this electron bombards, so there will be two electrons out. So this molecule become ionized. So one of the bonded electron is ejected out. So this is a radical cation. This radical cation is considered to be a molecular ion. So in the first molecular ion will be detected, and then this particular radical cation goes into the fragmentation, and we will get cation, radicals, neutral molecules, and radical cation. So this process is combined in the instruments, and you will get the different fragments. Now let's see how exactly it happens. Now look at here. This is the methane molecules. When this methane molecules is bombarded with the one single electron with the 10 electron volt up to 15 electron volt energy, then what will happen? The octet over here, 8 electrons are there around the carbon. One of the electrons from this bonded will be ejected out by this electron, and the 2 electrons will go out. So when one electron is taken out, this overall molecule become ionized. When this molecule gets ionized, there is a cation, and this cation, one cation, and the molecular mass of this is 16. So 16 upon 1 will be 16. So M by Z will be 16 for this molecule, and this is considered to be a molecular ion. Now, when this goes into the magnetic field, then what will happen? The proton can be ejected out as a proton as a radical, and the remaining is a methyl cation. That methyl cation may show methyl M by Z as a 15, 1,5. So that way fragmentation will proceed. Now, if you see the another examples, now look at here ethane. Now this ethane, when bombarded with a single electron, it will taken out one electron. This overall molecule become ionized. Now this ionization takes place, maybe carbon hydrogen or maybe the carbon carbon. This depends. Now suppose we consider this ethane molecule is ionized across this carbon hydrogen over here. This is the ionization. So one electron has been removed. So overall molecule is considered to be a molecular ion. So this M by Z is 30. 15 plus 15, that is 30. Suppose one of the H has gone out. So this H radical has gone out, and this ethyl carbocation is left. So this mass is 29 because one H is lost. So M by Z is 29. Suppose this ionization is in between the carbon over here. So this ionization is takes place over here. So that means this overall molecule become hemi heterolysis. That ionization is because of the hemi heterolysis. There is a homolysis, there is a hemi-heterolysis, there is heterolytic cleavage. So that type of cleavage are possible. But here, whatever charge, radical and cation is there. So separation of this radical and cation is because of the hemi-heterolysis. So this hemi-heterolysis gives you the cation as a methyl cation and a methyl radical. So this methyl radical will not be detected, but methyl cation can be detected in the spectrum as a M/Z15. So this methyl ethyl as a molecule can show M/Z30, that is the prominent peak, which is the first peak in the mass spectrum, whereas the second peak will be your methyl, second peak will be the ethyl, then methyl, and then H. So you will get how many peaks? 1, 2, 3, and oh, sorry, not radical will be not showing over here. So the carbocation will be this one, and this one. 3 peaks will be shown in the spectrum. So from that spectrum, you can easily work out the methyl or ethyl or sort of peaks. Now look at here. This is the ethanol peak. This is going to be a M+. Now here, the highest peak in the spectrum, the highest peak, absolutely 100% intensity. So this is intensity versus M/Z values. Now this is considered to be the most stable peak in the mass spectrum, most stable peak. Now suppose we have ethanol, the oxonium is considered to be a cation here, and that is CH, this will be like CH2 double bond OH plus. So this will be the peak for this. And this peak is considered to be a base peak. That means this is considered to be a more stable peak. So the most stable peak in the mass spectrum will have the 100% intensity. That means it is the tallest peak in the mass spectrum, and that is we called as the base peak. Let's see the another spectrum. Now, what are the things further need to know? That most of the elements, they're having a natural isotopic abundance. Now, if you see here, the carbon normally will have one isotope as a mostly from 1%, that is C13. So M plus 1, that means the mass is 13. That means isotope, if it is 12, that is a C12. And if you are getting the C13, that means M plus 1. If there are certain isotopes having, like take the example of halogens like chloride will have two isotopes. Which are those isotopes? One is 35, another one is 37. So 37 is considered to be a +2. That means 35 is considered to be a prominent peak. So +2 is nothing but your M+2, that is the isotopic peak. Similarly, there is a bromide peak. There is another isotopes which will show the M+1, M+2, M+3 type of thing. Now look at here the example, the best example of M+2. So this is a bromide. Now this is 2-bromopropane. So this first peak, now look at here. The first peak is M+2 because the 2 units will be more. The intensity of both the peak is same because the abundance in the nature is 50-50%, almost 50-50%. That's why the height of the peak is almost same. So the intensity wise both are same. If you see the chloride, their intensity is 1:3. One is heighted one, another one is small because it is 3:1. Now here it is 1:1. So one will be the molecular ion peak, another one will be the isotopic peak, that is M+2. So for the bromide, there is a possibility to have M plus M+2 because of these two isotopes. There is 79 bromide and 81. So these are there is a difference between the two units of the mass. Now, this is considered to be a base peak because it's the tallest one, and that is obviously the propane carbocation, which is under the isopropyl group. Actually, after rearrangement, it will give the 43 units. That is considered to be the most stable. Let's move on to the next. Now, chloride, as I said, this is again having the possibility to have M+2 because there are the two isotopes, that is 35 is the M plus, and 37 will add it 2. Now here 35 is in 75%, whereas the 37 is considered to be 20%. That's why the intensity wise they are indifferent. So if you see the another peak over here, if this will be cleaved, you will get the aromatic peak. So this 77 is considered to be aromatic peak. So the chlorobenzene mass spectrum will be look like this. So there will be two M plus values. One is isotopic, another one is your base molecular ion peak. More to the next spectrum. Now look at here. There is a very much famous nitrogen rule. What is the nitrogen rule? If the compound contain an odd number of nitrogen, so the overall mass of that particular molecule will be odd. If the even number of nitrogen is present, the overall mass of that particular molecule will be the odd, will give the odd mass, odd number of nitrogen give the odd, and even number of nitrogen give the even number of mass units in the mass spectrum. This is related to the nitrogen rule, which is already you know this sort of thing, but you will get a crucial information about the structure because of this odd and even number. Now, another easy thing to understand, whenever there is a iodine present in the molecule, so there is a gap in between the peaks observed, because you can see this mass is 127. Whatever alkyl groups will fall, they will fall further down. So the gap will be huge, and that gap indicates there is the presence of iodide in the molecules. Now, most of the molecules will undergo fragmentations, and that fragmentation in terms of a simple methyl group will go off, ethyl group will go off, propyl and butyl. So whenever sometime in the spectrum will be given M plus minus 15, that means loss of methyl group. If there is a M plus 29, that means ethyl group will be lost in the molecules. If there is a propyl group, that means M plus minus 43, M plus minus 57, that is a butyl group. So these are the some of the trick to understand. Sometimes you have to take the difference from molecular ion peak. Suppose molecular ion peak is 100 and you are getting the peak at something like 85. So that means there is M plus 15. If you are getting like 100 minus 29, like 71, 100 is a molecular ion peak, and then 71 is your another peak. That means there is a M plus minus 29. So sort of informations you will get it from the mass spectrum. So if you see here this example over here, so this 2-methyl pentane where the molecular weight is 86, so this is M plus. So this M plus is lying over here. Now this M plus will lose 15 units. So 86 minus 15, that is 71. That is M minus 15. Now again 29 units have been lost from this molecular ion peak. So M minus 27 is 57. Then again M minus 43 is 43. So this is 43 is the another isopropyl group. So this way you can easily work out the fragments directly from the molecular ion peak. Now look at here. As I told you, the abundance, that is a natural stability of any fragment, gives you the base value in the mass spectrum, the base peak, the highest or the tallest peak. Now, if you see here, the structure which is having olefinic compound, where this olefinic compound will show the loss of ethyl group. With the loss of ethyl group, there is a carbocation across alpha to the olefin, and that show you some resonance. Now this resonance actually here, this shifting of the positive charge from here to here gives you the more stability to this fragment. So this fragment is considered to be a base peak in the spectrum, where this is considered to be where ethyl group is lost. That means if you minus 29 from this 84, you will get 55. So this is a simple understanding how you are going to read the mass spectrum. Now look at here. If there is an aromatic ring present, that to benzylic type of fragment is there, the CH2 attached to the aromatic ring. So that CH2 attached, that is we call as benzyl carbocation. This benzyl carbocation will spontaneously undergo the rearrangement, and that rearrangement goes into the tropylium cation, and that tropylium cation is considered to be unique identity of the mass spectrum. Whenever you get the 91 peak, 91, you have to understand your compound possesses the tropylium ion, and that tropylium is one of the tool to identify. So whenever you will have benzyl carbocation, that benzyl carbocation will show you the 91 peak, and that is the base peak always. And that base peak will be clearly giving the information about the benzyl group. And this way, you can easily read out the spectrum. Now look at here, if you're having an aromatic ring, and this aromatic ring undergo fragmentation, and you will have 77 fragment. So this 77 fragment indicates that there is a presence of aromatic ring, and that aromatic ring gives the information about the structure that one fragments will be confirmed. So this way you can easily work out. So you have to remember the values 15, 29, 43, 57, then 77, 91. These are the prominent values which gives a very easy information about the structural fragments present in the mass spectrum. Now, whenever there is alcohol present, like hydroxyl group present in the molecule, the hydroxyl group is very sensitive because some point it may go out as a hydroxyl group, or it may undergo dehydration. So it may lose the water molecule. That water molecule is minus 18 if there is a dehydration. If the hydroxyl group go out, then there is a M minus 17, that is a loss of OH group. So most of the time, the hydroxyl group go out as a radical as well as water molecule. So you can easily work out that M minus 17, M minus 18. In case of most of the alcohol, the oxonium ion, that is CH2, what is oxonium? That is we call as CH2 double bond OH plus. So this oxonium ion is considered to be a most stable fragment in alcohols. So this is oxonium ion. Whenever there is a alcohol, so this alcohol undergo the fragmentation, and you will get a 31 as a prominent peak, sometimes is a base peak, and that you must understand there is a oxonium ion present. Whenever there is alcohol moiety or alcohol possibility as alcohol as a molecule, so you have to think this fragment too, or some point it may lose a water molecule or hydroxyl group. So these are the some of the informations to characterize this spectrum. Now look at here the how it will works. Now if you see here propanol, so this propanol when spray in the mass spectrum, it gives you the molecular ion peak, no doubt. There is another peak called as M minus 18. So this M minus 18 intensity is very less, but it is possible. There is a loss of, because we are going to put in a very high energetic zone. So water molecule is the possibility to eliminate it from the molecule. So this may be the possibility. Another possibility that this molecule may cleave over here and the radical from here and here, because already the oxygen will lose the lone pair of electron and we will have a cationic species. And the moment you will get the positive charge and the dot on the oxygen, the alpha bond particularly, this will cleave, and there is a possibility to have this fragment, that is oxonium, and that is again the base peak in the alcohol having molecules. Look at here some of the amines. Now, as I told you, the nitrogen rule. What nitrogen rule says, if you have odd number of nitrogen, the mass of the molecule will be odd, or if it is even, then even. But in case of amines particularly, the formation of iminium ion, that is after the alpha cleavage, the lone pair of electron from the nitrogen will be loose, and there is a formation of iminium ion, and that iminium ion will have the odd number. It's supposed to be even number, but molecular ion will have an even number because you are going to lose the even number of fragments. So that's why the remaining is considered to be even number. So most of the cases, amine will give the iminium ion, which is having the even number of the mass. Now take this example to understand. Now look at here. This is some sort of amine. When this undergo the fragmentation, you will get the M plus, and then you will get 86 and 72. Now this 86 and 72 is because of, look here, 72 when it will lose this fragment, and when it will lose ethyl group, you will get the 86. Both the cases, the ethyl and the propyl group will be lost, and less resultant will be iminium ion, and that iminium ion will have both even number of fragments, and that indicates there is a formation of imine. Now, if we having ether in the as a molecule, particularly the ether normally show the cleavage. No doubt this will be the molecular ion peak, but this molecular ion peak will undergo the alpha cleavage and forming again the oxonium ion, because most of the cases the positive and dot will be on this oxygen. And when the alkyl group will be cleaved, so this will go out as a radical, and this radical will form a double bond over here, and that will form oxonium, which is a choice for ether as well as alcohol. And this is going to be a prominent peak in the mass spectrum. Again, same thing, the alkyl group directly attached to the oxygen will not cleave, because the radical which is formed as a oxygen having a radical, which is considered to be highly unstable and which will not form. So oxonium again is the choice of formation in case of ether too. Now look at here, this example. This is ether. Now the molecular ion peak is 74, and then when one methyl group is fragmented over here, so there is a formation of double bond across this, and this will look like this oxonium, and we will have this peak. Further, this side, if I lose, like, look at here, if I remove now another height, what we have done here. Now, this is another oxonium ion. Okay, so first we have removed 15 units. That means methyl group has been lost. Then we have this, another methyl group will be lost. So what you will get? You will get some point this fragment. Now, this is oxonium having CH2. So this CH2 further will lose, and there is a formation of this type of oxonium, because this is there is a rearrangement sometime. So 31 is the prominent peak, and 45 also. So these are the possibility to have the loss of the alkyl group resulting into the oxonium. Most of the cases of ethers and alcohols, oxonium is the choice of fragment. In case of aldehydes and ketone, again, the acylium is going to be a choice of formation. Now look here, this is aldehyde. So this hydrogen, if goes outside, so what it will form? It will form acylium ion. And this acylium is considered to be a stable peak. And that sometime it will be showing M plus minus 1, that is a loss of your hydrogen. Or if it is a ketone, or if it is like a aldehyde, like take the example of, we can say here RCHO. Suppose R going as a positive, so this will be going radical. So this aldehyde group, if it is lost, it will be 29. So it may be sometime minus 29. So the CHO mass is 29. So sometime you will get alkyl group if it is a ketone. If it is aldehyde, there is a possibility that if we having this type of thing, so sometime this H will go out, sometime the R will go out as a cation. So that's why sometime you will get minus 1, sometime you will get minus 29. Minus 29 means CH. Now look at here, you will understand from this example. Now this is your aldehyde. So 2,3-phenyl propanol. So this 3-phenyl propanol, when treated with mass spectrometry, so this is a molecular ion peak. So if you take the difference between this is a 29, that means aldehyde peak will last over here. So this aldehyde will off, that is minus 29. So this peak is because of rest of the thing. Now, if I click over here, this is a troponium ion. So this is a troponium, that is the most stable one. Another possibility is what? Because troponium is another choice, as well as this loss of the aldehyde. So these are the prominent peak possible in case of this type of aldehyde. If it is a ketone, again a similar type of thing, the alkyl group will lose, and there is a formation of acylium. And look at here, This is acylium for this 2-pentanone, and this is going to be a base peak for this acylium, and this is another peak for the acylium 2. So M+1. Esters are also showing the similar type of thing. There is a loss of OR. That means the carbonyl group is having OR. That group will be lost, and sometimes there is a loss of R2. So these are the two possible cleavages. Now look at here. This is an ester. Now if I would say there is a loss of, this is M plus, and this M plus will lose this methoxy group. So you will get 105. And if this will cleave, so this is a benzene ring. So this is possibility to have the cleavage over here or here. So you will get prominent peak 105, 77, and this is N+1, N plus value. So this is a hydrocarbon. So just like a pentane or hexane type of compound, what will happen here? There is a loss of methyl group, maybe the ethyl group, then the propyl group. So that's why there is a, if this is a M plus, if you lose 15 unit, you will get this one. If you lose 29 unit, you will get the 43. And if you lose the rest of the 43 units, you will get the 29. So this way you can easily show this possibility of fragmentation. Now look at here the spectrum, how the spectrum looks. Now if you see here the spectrum, just to understand how the analysis of mass spectrum will be done. Now I have written this mass spectrum on the top here. Now you can see here the values. What are the values? I can take some of the spectrum down now for understanding. Now, if you see here, this is a molecular ion peak C8H7N. Now, from the molecular formula itself, you can consider there is a one nitrogen present, the M plus will be odd number. So this is odd, 117. So this is one thing is clear. There is a two peaks, prominent two peak, 91 and 77. What this indicates? There is a presence of troponium ion as well as the benzene cation. So the benzene ring is present as well as benzyl group is present, and rest of the molecular weight is this. So if you minus from 91 to 170, you will get the 26 unit. And what is 26 unit? You can just easily work out what left. And that sometime from mass spectrometry, you can easily work out the structure too. But if you are having a supporting data, that will be more useful, and then easily you can work out what is the structure of the molecule. So this is all about the mass spectrometry. So from tomorrow onward, we are going to take such types of examples to study or how to read the spectrum, how to characterize the spectrum, how to elucidate the structure of the unknown molecular formula, the structure, their name, their fragmentations, and characterizations as a whole. We are going to see one by one. We will see a couple of spectrum from a very standard book, and definitely you will enjoy the reading the spectra and characterizing the unknown structure. I hope you are enjoying. So tomorrow we will start the actual understanding how to read the spectrum. So this is all about for the day. See you tomorrow. Thank you.